Now, toroid. So, toroid is a hollow circular ring on which large number of turns of the wire are closely wounded. Okay. So, it can be viewed as a solenoid which has been bent in a circular shape. Means, suppose we have a solenoid and it is bent in a circular shape and end to end it is closed, then we can say it is the toroid. Okay. Now, here, suppose as shown in this figure, this one is the toroid and figure B shows the cross section of it. So, here, outside the solenoid as well as outside the toroid, the magnetic field that is zero. Outside means here point P that is outside the toroid, point Q that is outside the toroid. So at any such point, the magnetic field that is zero. Okay. But here inside the toroid, at any point means in the space inside this wounding, right? The magnetic field that will be uniform one, constant one. Okay. Now let's derive the equation for this uniform magnetic field in the toroid. Clear? Now equation for magnetic field inside the toroid. Now see, this one is the toroid and we want to find the magnetic field at any point inside the toroid. So here consider three different Amperian loops. Two are in the exterior part of it and one that is inside the toroid. See, first we think about this Amperian loop 1. Now see, for this Amperian loop 1, the current enclosed by this loop, or we can say current passing through this particular loop, that is 0, because entire current that is outside it. So magnetic field that is 0. So here in this particular region, at any point, the magnetic field that is 0. Now if we consider this third one, this one is the Amperian loop. Now Amperian loop that is enclosing a surface. So if we consider the surface, which one is cross section of the toroid, then for this particular loop, see the cursor here. Suppose here the winding that is going inside of that surface, then from other side the winding is coming out, again going inside, coming out. So here if current I is entered to this one, then through each turn we can say current I is flowing. But if we think about the surface enclosed by this Amperian loop 3, then I current enter to the surface, I current leave the surface. I current enter to the surface, I current leave the surface. Now suppose here total number of turns in the toroid, that is capital N. Then total current Ni enter to the surface and total current Ni leave the surface. So net current passing through the surface, that will be again 0. So magnetic field at any point outside this one, that is 0. Clear? So for first Amperian loop, the magnetic field at any point, that is 0. For third one, that is also 0. So in general, now we can say outside the toroid, the magnetic field is 0. Clear? Now consider the Amperian loop 2, which one is represented here by blue dotted line. Now see, here if we consider at any point the direction of the magnetic field, then that is tangential to the loop, and the line element dl, that is also tangential one. So for second Amperian loop, we can write the Ampere's circuital law, integration b dot dl, that is mu 0 sigma I, integration b dot dl, that is integration b dl cos theta. Theta is 0, so cos 0, because b and dl both are tangential to the loop, so in the same direction. That is equal to mu 0 sigma I. Now b is the same one, uniform one, so taken outside the integration. So b integration dl, that is mu 0 sigma I. Now integration dl, that integration we have to carry out over the circumference of the Amperian loop. So that is the 2 pi r, where r is the radius of Amperian loop. So we can write here b into 2 pi r, that is mu 0 sigma I. So here through each turn the current flowing, that is I, and total number of turns, that is capital N. So we can write sigma I, that is Ni. Now take this 2 pi r on right hand side. So here N upon 2 pi r. So total number of turns divided by total length on which these turns are distributed. So that will give you the number of turns per unit length. So here in 2 pi r length, if the total number of turns is n, then per unit length how much? So with this unitary method, you can understand the number of turns per unit length, that is n upon 2 pi r. So replace this n upon 2 pi r by small n. Again, you will get b equal to mu 0 n I. So toroid, that is nothing but a long solenoid, because when the solenoid is made in the form of circle, end to end it is joined, means now it is endless. Clear? So magnetic field inside it, that is uniform.